we had in the lab, and I am including here the link to the Google Doc for the lab, and also a link to the whiteboard in case we need to do some analysis. Like we said, today's class will be on polarization analysis, how we can study earthquake sources and how we can study the medium through which these waves propagate by understanding polarization of seismic waves. Again, I hope you're all on board. If you have any questions, put it on the chat box. Someone will relay that question to me. Just a point of note: if you see a pink board like this means to pause, to reflect, to review, or to engage with me. So if you have questions, this is an opportunity for just to ask those questions. So are there any questions? I'll wait for a couple of seconds. I don't think there are any questions. So I'll give an overview of what we're going to learn today. In the beginning, we'll talk about wave polarization in general. So wave polarization 100 or wave polarization 001. We'll review the fundamental math behind, or physics behind seismic wave polarization in particular. And then I'll go over some applications, trying to draw out basic general principles and methods that we can use to identify or compute seismic wave polarization. I'll give applications on land, on our planet, the Earth. I'll give applications on sea, on the ocean bottom, on our planet, this Earth. And I'll also give applications on planets far, far away. Actually, not too far away, planets in our solar system. That is Mars. That's the only other planet, apart from Earth and the Moon, that we've actually placed seismometers on. And then I'll do a debrief, preparing us for what we'll be actually learning practically in terms of writing Python scripts that will drive home some of the ideas related to the lecture. So that's kind of the overview of what we're going to be learning today. Wave polarization in general, the fundamental physics and math, helping us to understand the notation and concepts. I'll go into application, general principles and methods, on land, on sea, planets far, far away. And then we'll dive in to learn in practice. Okay. So, seismology. You're all seismologists, emerging seismologists, and if somebody was to ask you, what does a seismologist do? You might answer like this. I often answer like this. Well, seismology, or planetary seismology, is the study of elastic waves, i.e. ground vibrations, that propagate through the planetary interior and gives us information about the medium through which those waves propagate. That medium is the rocks that our planet is made of. And also gives us information about the sources that created these ground vibrations. And in most cases, those sources are earthquakes, but often, more often than not nowadays, is active sources or just ambient noise, just the planetary, our Earth's vibrations over time. So you have a source over here, it propagates through a planet, oftentimes that's the Earth, but this is an illustration of, say, for example, Mars, and you have somewhere, hopefully, a receiver, a seismometer that will measure that vibration of the ground, and through the inertial principle, you record on a seismogram different kinds of waves, P waves, S waves, surface waves. And by inferring travel time often, the travel time information of this wave, or the arrival time information of these waves, you can say something about the medium and the rocks to which they propagate. In this lecture, we'll learn how we can glean a lot of information about the sources and the medium from focusing on the polarization. Okay, so let's move ahead. The very first thing for us to kind of hammer home is the idea of classifying different waves. So you're looking at two waves here on the screen, and the question I want you to answer is, how could you classify these two waves? They look different, but they are, in general, just waves. So what's a wave? It is a disturbance that transfers energy. So for example, we have an elastic wave, which is a ground vibration, a disturbance in the medium, transferring energy. So the medium itself moves, but the wave moves outward from the source that generates it. So there are two ways we could classify these two waves, right? So this wave is totally different from that wave. The question is, what class of waves is this? And what class of waves is this? What is different about this wave in terms of the movement of the medium and the movement of the wave from this wave in terms of the movement of the medium and the movement of the wave? I'll pause for a bit to take feedback. If you have any answers, first two answers will help us kind of move on to the next slide, but I just want you guys to kind of pause, ponder, reflect, and engage.
There's a question in the chat.
Yes, I'm just waiting for Francesca. I think Francesca speaks for the class. So there's some feedback in the chat.
Oh, okay. So the question is the particle motion parallel and perpendicular to the direction of propagation? And
exactly.
Then
go ahead, and then someone says?
Someone said displacement and wave propagation direct.
Good, great. You guys are getting at the key of the way we can classify waves based on based on how two things relate to one another, right? Based on the motion of the matter, the particle motion of the medium, and also the motion of the wave. So the key idea that you guys have kind of drawn out is one, this wave is of one class called longitudinal waves. That is, the particle displacement is parallel to the wave direction, right? And this wave is of another class, transverse. Here, the particle motion is perpendicular to the wave direction. So the relationship of particle displacement to wave direction gives us a way to classify waves. And so that's what we're going to be looking at here. We've essentially gotten this essence of wave polarization. And so in our case, then we'll be asking what is the direction of particle displacement? What's the direction of wave direction? What's the direction of the wave motion? So the wave vector, and how does these two relate? So I'm going to give you examples in nature. You already know these examples because if you can interact with the sense with the world, then you've experienced this different kind of. So, for example, sound. You can all hear me either through the speaker, but this is an example of a longitudinal wave. The pressure motion, gas molecules move in the same direction of the sound of the wave, right? So, particle motion is parallel to wave direction. Light is an example of a transverse wave. Whatever it is that's vibrating the electrical field and the magnetic field is perpendicular to the wave direction, right? So light is a class of transverse waves. And actually, water waves, especially in the ocean, is an interesting, intriguing class, which is essentially coupled waves, coupled longitudinal and transverse, as you can see in the illustration. So in nature, we've got waves of different classes polarized in different ways. Longitudinal, transverse, and coupled, sound, light, and water. So what are wave polarization through the solid Earth? When the ground shakes, either through an earthquake, and waves are generated, how do those waves radiate out, and what polarization do those waves exhibit? Before we start, let's just do a quick review of geometry. So, often on our planet, on the Earth, we can specify location by two numbers, longitude, phi, and latitude, theta. And then you can calculate the distance between two locations on the surface of our planet. So here is, say, for example, a station, and here's the location of an earthquake, right? So two dots, one station, one earthquake. And then you can measure the distance, delta, arc distance, delta, by just this formula here, which is a function of the station longitude and latitude, and the earthquake longitude and latitude. And that's the geometry of that situation. Here, you can also measure the azimuth, right? So the earthquake travels along a direction where the angle xi, clockwise from north, is the azimuth of the earthquake. And that azimuth is given by this equation as well as a function of the distance and the coordinates of stations of earthquake. So just to remember that. So on our planet, if you've got an earthquake here and a station there, there will be an azimuth that the earthquake travels along the great circle path between the earthquake to station. And relative to this azimuth, there's another angle called back azimuth, xi phi, that is just the alternative. So looking at the azimuth from station to earthquake. So to review, earthquake azimuth, earthquake to station azimuth is xi, earthquake, station to earthquake back azimuth, xi prime. So when the wave propagates along the great circle path from source to receiver, if you look along the radial plane, so this is the radial plane, the source to receiver radial plane, we'll see three classes of waves, polarized in unique ways. So this is polarization of waves traveling through the body of the Earth, arriving at the receiver, propagating from the source. You've got an SH wave, an SP wave, and a P wave, compression wave, with those polarizations. On the surface of the Earth, we've got two types of surface waves, log and Rayleigh. Essentially, these two surface waves are trapped on the surface of the Earth, so the amplitudes decay as you go radially into the Earth. And the log wave is a class of SH wave trapped on the surface of the Earth, and the Rayleigh wave is a coupled PSV wave, polarized in that sense, trapped on the surface of the Earth. So these are the polarizations of these two classes of waves, body waves and the surface waves. Okay.
Dr. O?
Go ahead.
I had a question that's always bothered me, and that is, imagine we have a vertically incident shear wave. How do you define SH and SV in that case? Like, it's easier for me to look at this and imagine why they're defined as such. But is there a convention that would allow you to determine those?
Yeah, go ahead, finish the thought.
Oh, that's all it was.
Yeah, so you always for shear waves, you always want to keep in mind the wave direction, so that K. The wave direction gives you the SH wave, and along the wave direction, the SH wave will always be orthogonal to the wave direction. And so if you think about it if you imagine your mind's eye, a wave, starting off at the source, it will start off with the incidence angle, but it will bend. It will get to a point inside the Earth where it reaches a post-critical incidence angle, and then fully reflect inwards, right? But at every point along that path, the SH is always orthogonal to the wave direction. And that's the way you kind of keep that in mind. Is that helpful?
Yes, thank you.
Yeah, okay. Good question, and I encourage questions. If we answer questions and not finish this lecture, it's way better than me just finishing the lecture and no questions answered, right? Okay, good. Let's proceed. So we've seen examples in nature. How about examples in seismology? I've shown you in the slide before. This is then a longitudinal wave. This is a compressional wave. It is exactly sound traveling through solid. So P waves are sound traveling through solid. So compression waves traveling through solid. Transverse, go ahead.
We have a question before we move forward.
Yeah, proceed.
So the question is, in the case of vertical incident, are SV and SH indistinguishable?
Oh, they are distinguishable, right? Because the SH and the SV will always be orthogonal to one another while still being orthogonal to the wave direction. I hope that helps. So there are two planes. Two planes are orthogonal to the wave direction. One plane will host the SH, and the other plane will host the SV. Now the key with one another is SV will always be in the plane of the wave direction. And does that help? Or does anybody have a better way of kind of describing what I just said?
The person who asked the question said that helps.
Okay, great, good. Thanks for that question. So again, in seismology, we got compressional waves, P waves, those are longitudinal waves. The particle motion will always be parallel to the wave direction. You got a shear wave, right, the transverse wave. So the particle motion, in this case, is orthogonal to the wave propagation direction. And then you got a surface wave, right, a Rayleigh surface wave, which is a coupled longitudinal and transverse wave trapped on the surface. So example, compression is like sound, shear is like light, and Rayleigh waves are like water in that sense, in the sense of their polarization. Okay, moving ahead. So, it will not be an advanced seismology class if we did not show seismic wave equation. So this is the seismic wave equation. You've probably seen it before in your seismology class. It is equation governing wave propagation in a solid earth, mostly elastic wave propagation. So U is the displacement at any point X and in time T. And you've got essentially the acceleration of the wave here governed by this vector calculus relationships. Essentially then you have a displacement field that can be separated into two potentials, two components. The P potential, which is this phi function, which is essentially a scalar field. And this potential, I don't know what this interesting Greek letter is, so I'm going to try to pronounce it, but it is a vector potential describing SV and SH propagation, right? So the displacement field has two components, P and S, where S is SV and SH, just like I just described. So if you then take the divergence of this seismic wave equation, everything falls out. I mean, everything except the P potential falls out, and you have a P wave seismic wave equation traveling at the speed alpha. So this is a wave equation just showing the P traveling at speed alpha. So that happens when you take the divergence of the wave equation. If you take the curl of the wave equation, things happen to any field that looks like this, the divergence of a curl or the curl of a graph. All those fall out, and you have a wave equation that separates out the shear waves, the SD and SH waves, in an isotropic media that will have speed beta. In an anisotropic media, this is a little more complicated. So that's the transverse wave. That's how the transverse wave falls out of the seismic wave equation. For a coupled wave like a Rayleigh wave, you will have P and SV coupling. So you have a potential phi for P and a potential, I don't know what this Greek letter is, but this other potential for the SV wave. They will travel at the same speed and the same wavelength. Sorry, they will travel to a particular phase speed at the same wavelength and the same wave number k. But then if you impose some boundary conditions, say, for example, that the wave should be trapped in the surface, so this potential must be negative and decay with depth z, and that there's no traction at the surface, and you do all the algebra, painfully do all the algebra. These two equations pop out for the displacement in the xz direction. And here you notice that the ux direction is sine, it's a sine function, and the uz direction is a cosine function. Essentially, x and z then exhibit pi over 2 phase shift. Essentially, that's what you're seeing when you see this elliptical motion are described in the coupled waves. So that's longitudinal waves, transverse waves, and coupled, in this case, really surface wave, PSV, coupled waves. And how they...
We have a question.
Go ahead.
It says, for a coupled wave to exist, do the components need to have equal frequencies?
Yes, they have to have equal frequencies and wave number, yeah. So essentially, that would be propagating coupled in time and space, right?
So, and we have one more question before we move forward. The question is that some books say that the solution for the P wave is displacement, while the solution for the S wave is potential, and they are wondering if you can clarify that a bit.
You can always go from displacement to potential, right? So this tells you that this displacement is the grad of the potential and the curl of the potential. So if they tell you that it's potential, then you can always get back to displacement. If they tell you displacement, it's really a function of potential, right? So that's kind of explaining it. So one or the other, it's okay. But just so you know, right, if you're looking at the compressional, every term that is curl falls out. And if you're looking at compression, yeah, and if you're looking at shear, every term that is P potential falls out, right? I hope that explains that. Is that person satisfied?
Yes, that person is satisfied, but we have another follow-up question.
Shoot.
So the follow-up question is, what is the physical significance of using potentials in the decomposition?
I actually, that's the first time I thought about that question. I bet it's so that you can write out these expressions where you're separating the behaviors of the P and the SV, knowing that when you take divergence and the curl, they're going to draw. I'll just say it's probably a mathematical tool, but it's a helpful mathematical tool. But I'll look that up and get back to you as well. Susan, do you have any thoughts on that?
Not at the moment, sorry.
No problem. Okay, great. So let's move ahead. So let's look at actual seismograms, right? So oftentimes you will have your seismogram in three-channel seismogram, vertical, north, and east. So for now, if you just ignore the vertical channel and we look on the horizontal plane, you've got a north-south channel recording a seismic wave as it arrives. You've got an east-west channel, right? But then if you rotate into the direction, this theta direction, into the back azimuth or the radial direction, so that's 180 from the azimuth or back into this direction, you can take the northeast channel and rotate it into the radial transverse channel. That's what's being done here for this particular earthquake that's coming from this distance, at this depth, from this region, Mariana, on this station. This is what the earthquake looks like in the north and the east. And then when you rotate into vertical radial transverse, this is what it looks like. Now then, all these different phases are polarized in a unique fashion that you can then interpret. So let's look at what that polarization looks like for two types of seismic phases: SKS, SKKS, and SDIF. So if you take after rotation into the radial transverse plane, this SKS, SKKS phase, and you just plot how the ground is moving in the horizontal plane after rotation, that is in the radial transverse direction, you notice that this SKS, SKKS phase is polarized in the radial direction, right? It is most of the motion is in the radial direction that way, but there's a slight motion in the transverse direction, imparting onto this phase some ellipticity that you can see. So in this case, the SV, the SKS, SKS phase in the SV is an SV wave. For the SDIF, most of the motion is in the transverse direction, a slight motion in the radial direction, and essentially this is the SH wave. Any question?
No.
Okay.
We can keep going.
Moving ahead. So that's S waves, seen their polarization after rotation. Also, like your attention to the radial wave, right? So that's the radial wave there coming after the love wave. You notice this is radial, transverse, vertical. As you can see, the radial is polarized on the vertical and radial, so it's on the vertical and radial, while the log is on the transverse. But if we focus in on the radial and we just plot, zooming to the radial wave time, you will notice that the radial wave is elliptical, so it's polarizing that direction right there, where the vertical motion is maximum. So UX is, sorry, UX is the radial direction. So UX is maximum when UZ is minimum and follows that phase relationship going ahead. So essentially, the vertical and the radial have a pi/2 phase shift to them. This is actually diagnostic of a radial wave. So if you computed the, say for example, Hilbert transform, and you notice this behavior, you can tell that it's a radial wave, but also if you rotate in such a way that this behavior can be described mathematically, then you will know the radial direction, incoming radial direction of the radial wave. This is very useful in seismology for doing a couple of things that I'll describe in a few. Okay, so moving ahead. So let's go to practice. So we've seen the basic physics and math, giving examples in nature, examples with seismic waves. Let's look at how this is used in practice. Applications of seismic wave polarization on land, on sea, and other planets far away. So let's start on land. So this is a paper by Ishii and Park, 2018, where they are, where these authors are measuring the incidence angle, the apparent incidence angle of a compression wave, of a P wave, and the incidence angle, apparent incidence angle of a shear wave. Now, how do they do that? They do that by using this technique called the covariance matrix method. This is a method that was, I think, first published probably by Geophysics in 1988. And essentially, you create a covariance, a 2x2 covariance matrix that is this formulated this way: this X transpose X normalized by the number of samples in the record. What is X? X is the vertical and radial displacement, d-mean, and then you use that X matrix to then create this covariance matrix. When you do a singular value decomposition of this covariance matrix, it will separate polarization direction into two eigenvector directions, VL. So there'll be two directions, V1 and V2. Those two directions tell you the wave propagation direction for P waves will be the maximum, will be the direction V1 that is maximum in the eigenvalue lambda 1. So essentially that's where most of the polarization is in. So therefore then the P wave direction will be in the direction of the eigenvector V1 associated with the maximum eigenvalue lambda 1. And you get that, you also get the P incidence angle for free, which is because the direction of V1 then is the incidence angle, apparent incidence angle of the P wave. Similarly, because there are only two directions, eigenvector V1 and eigenvector V2, for S waves, instead of using V1, you use V2 because S waves are polarized orthogonal to the wave propagation direction. So then the phi bar will be the direction of V2, and that's given by this expression here. So you can measure P incidence angle, S incidence angle from the covariance matrix, targeting the waveform at the arrival, P arrival time, and S arrival time. I'll pause for questions here.
Okay, so we have a question and we're waiting for some clarification, but maybe I'll ask it before we get the clarification. So in order to get the radial and transverse components, do you rotate with vac azimuth or with the incoming polarization from ZNE to ZRT?
Two great questions, and the answer is yes and also yes. So yes, you rotate with back azimuth if you have it. And yes, you can also actually formulate this as a three-dimensional covariance matrix That then gives you all the angles to begin with, right? But in here, in this two-dimensional problem, we're assuming that we know the back azimuth and that we have done a priori the rotation into the vertical radial plane. I hope that answers the question.
Okay, so then we have a couple of more questions. The first, I'm going to ask one, and then the question about decoupling, maybe that someone could clarify. And then in the meantime, the question is, which coordinate system, when would you want to use the LQT coordinate system?
Well, we'll get to that. The LQT coordinate system is just inside. So you've rotated now. That's if you know the angles, then you can do another, you can just do a rotation into that direction. So instead of your displacement being in vertical radial plane, so if I then, for example, take this theta bar and rotate it, and rotate then the vertical radial into the theta bar direction, then I'll be now in LQT coordinates. And you'll get an example of that actually in the lab. So this is a really great question that you asked. So just stay tuned for the lab, and we'll clarify the exercises in the lab. I hope that answers the question.
Yes. Okay. Great.
Okay. Thank you for all these questions. I really appreciate the questions. It means I am not alone and that you are following along. Again, just to remind you, if you have any questions at any point, please feel free to ask. It helps me kind of clarify points that might be difficult. Okay, moving ahead. So these authors use this measurements to quantify near surface velocity, because it turns out that the apparent incidence angle of P wave theta bar and the apparent incidence angle of S wave phi bar have a special relationship with shear velocity and compression velocities in an isotropic media. And so then if you measure this, if you make these measurements for tons of earthquakes that have different rate parameter P, you can then do a grid search for compressional velocity alpha, near surface compressional velocity alpha, and beta. And this they do, showing the histograms here of alpha and beta across the whole of Japan that has a high density network, right? And so this is fun. So you can actually measure near surface velocity by, you can actually constrain near surface velocity by measuring P and S with polarization. You can imagine that this is useful for engineering purposes. You want to know portions of the Earth that have low shear velocities, because these portions will essentially vibrate more, they'll experience more resonance. And so if you're gonna have buildings, you want to make sure these buildings are sited and built to withstand such resonance behavior. So it's a cool application of polarization analysis. Okay, another application of polarization analysis is for orienting a seismometer. You will think that this is redundant, but it's actually not. So imagine on our planet, it's probably not hard to imagine. You probably know this, you've probably been to the ocean. Our planet is 70% water. And so if you want to do planetary seismology on our planet, we have to go out on ships like this, drop seismometers from the boat, and then they land on the bottom of the seafloor, sometimes almost far down as 5 kilometers. And you do not know what the orientation of the horizontal channels are, because you cannot see them. Right? You cannot see where north is relative to the north on the seismometer. So using wave polarization that helped us actually, and has helped seismologists orient seismometers for a long time. So how does this work? This works in a variety of methods, but I'm going to focus on the radial wave, the approach using radial waves. So what is the direction? So the question we're asking ourselves is, what is the direction of the H1 channel? If you were on land, then you could just look at it and make sure H1 points north, and that's it, done. But on the bottom of the seafloor, on the bottom of the ocean, the seafloor, we do not know. So how do we do this? We know we can retrieve measurements for H1 and H2, and then we wait. We wait for a radial wave to come through, a surface wave, a radial surface wave to come through. Because we know that the radial wave will be polarized in the radial direction, we can then find that radial direction alpha and back out the delta, the true orientation of H1 from the measured alpha and our understanding of what the source receiver back azimuth is. So how do you measure this alpha? You measure this alpha by taking H1 and H2, rotating it via this rotation matrix, and getting a new H1 prime, H2 prime. And then you measure this coherence, this cross-correlation ZR. This is the normalized version of that cross-correlation ZR. But you can also kind of have this unnormalized one, CZR. This is formed by the zero lag cross-correlation of Z with R and the zero lag cross-correlation of Z with Z. Cross-correlation just takes two channels and forms this measurement. So Sij is a zero lag cross-correlation. And in our case, we're taking Xi and Xj to be the radial component and Xj to be the Hilbert transform vertical, right? Because we know that this is the expected phasing relationship between the radial and the vertical. And so then we measure the CZR, and we measure it for all possible back azimuth angles, this is alpha, until we maximize CZR. When we maximize CZR, we know, voila, we found the source receiver back azimuth, and then we do this, we back out from the source receiver back azimuth the true orientation delta. So this is an example of that process from these authors, where then you are looking at the cross-correlation value and the inferred delta from this Rayleigh surface wave at different periods. Any question? So now these authors then know that this channel, at this station, H1 is oriented 357 degrees clockwise from north, give or take. Any questions?
Oh, we do have a question. So the question is, do we have to consider the absolute or the real value of the Hilbert transform?
Absolute as in a complex number, absolute, or real value as in ignore the imaginary, right?
Yes, I would presume.
Yeah. I don't know, I have to look at the code to confirm that. My guess is that's the real value of the Hilbert transform, because it absolutely gives you the envelope, but I'll have to look at the code to confirm that. My guess is that's the real value of the Hilbert transform. Because that's the or real or imaginary value, because that's the, actually imaginary, because that's the one that's phased pi over 2 from the vertical. I think it's imaginary. But let me get back to you on that question. Definitely not the absolute, because that's the envelope. Whether it's a real or imaginary, I have to get back to you. I think it's the imaginary, because imaginary is the one that's pi over 2 phase shifted. That's kind of an answer, but not a complete answer. Any question or follow-up from that question?
No, I think that was a sufficient answer.
Good, good. Great, okay, so let's move on. Okay, good, so we've seen examples for near surface velocity, we've seen examples for orienting the seismometer. This is a very famous popular example for understanding anisotropy on the planet, so shear wave splitting in anisotropic media. So how do we do this? So for example, an incidence wave coming in this blue pulse interacts with an anisotropic media. Rocks are often anisotropic because the minerals are anisotropic, and the incident pulse essentially splits into two pulses. One is faster than the other, so there's a fast wave, fast S wave, it's called the QS wave, and there's a slow S wave, slow QS waves. And using the information of how the fast S waves arrive at the seismic channel, you can correct for the this behavior, this splitting behavior, and then infer the volume or the duration of time to which the incidence wave propagated through the anisotropic medium. So how does this look like in practice? You say at station RSON, you measure an SKS arrival on the north and the east channel. And this is what it will look like. You plot this SKS wave, the northeast component, it has kind of like an elliptical polarization. And that elliptical polarization is because you're getting a fast and a slow wave delayed from one another, impacting elliptical polarization to a wave that should, that was before it interacted with anisotropic media, linearly polarized, right? So then when you rotate into the correct fast direction, you will get this fast and slow wave separated by the time delay delta t. And so if you correct that fast and slow wave by this delta t, you can then adjust the polarization of the wave back into the linear direction. And so this is how then you can measure the fast direction and the delay time, which is often shown in shear wave splitting measurements. Any questions here? We'll get practice with these examples. With examples of shear wave splitting in the lab as well. So we've seen examples on land, on sea, examples for orienting seismometers, examples for studying anisotropic media through shear wave splitting. How about examples on other planets far, far away? This is one example showing how polarization analysis is used for seismic detection of the lunar core. So this was a paper written back in the day, I think in 1977, and how you can use the polarization of waves to stack, improve stacking of lunar quakes that can then tell you something about reflective waves off boundaries inside the moon. So say off the outer core, mantle, moon boundary, and stuff like that. So how does polarization help? Polarization analysis help in this case? You take a couple of events coming from location A6 on the moon. If you looked at individual seismograms that look like that, there's a lot of scattering. It's very hard to distinguish in separate phases. These are other examples from that A6 location. A lot of scattering. The moon is very, very, has high Q, scatters waves a lot. If you stack 53 A6 events, they might look like that. But then if you incorporate into your processing the idea that phases, P and S wave phases, should be polarized, should be linearly polarized, and you incorporate a modulator, a polarization filter into your stacking, you improve the stack of these 53 A6 events, and you get a stack that looks like that. It stacks where then the P and S wave phases and other reflections from, say, boundaries in the moon become clearly decipherable. So this is an example of how using polarization filters and array seismology helps you detect boundaries in the moon. In this case, these authors suggest the lunar core. Any questions?
We do have a question, but I think it's more a little bit towards the previous section than
Go ahead.
this. The question is, do we need to filter the signals in a very specific manner to check for these components?
To check for what now?
To check for, I think, the anisotropic.
Yeah. Yes, the answer is yes. Hope that helps. Okay, moving on. So that was on the moon, right? Our planet, the Earth, and moon, through the Apollo missions, are the planets where we've got seismometers listening to ground vibration. But I'm sure you guys have heard about a year ago or thereabouts, we sent a mission to Mars, a geophysical mission to Mars. And the payload on Mars was a very, 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 very expensive seismometer called called InSight. I guess this InSight mission called the SEIS package. And the SEIS package recently published results of the first detection of Mars quakes. Now the question you might ask is, but wait, we only have one seismometer. How can we know where the Mars quakes are coming from? Because maybe I learned in my seismology or my intro earth science lecture that you need three seismometers to triangulate the location of an earthquake. In this case, therefore, the seismologists, the Mars seismologists use one single station to infer the location of the Mars quake, identifying, and I'm going to probably pronounced this wrong, Cerberus foci, that location where there's faulting on Mars, as the location where the Mars quakes are coming from. How did they do that? You've got a very good long period recording here on the broadband seismometer, where they've identified the P and the S phases using some Mars interior velocity model and the delay time of this PS. You can measure you can infer the epicentral distance of this particular Mars quake. And then using polarization analysis, so just taking the P wave, the window of the P wave, and just plotting a huddlegram, just plotting a particle motion diagram, northeast, you can then measure the event back azimuth. And so if you know the distance and the azimuth, you've essentially done a range finding for the event. And they did it for all the long period low frequency events that they had confidence to call Mars quakes, and of the three of them gave them numbers that were kind of close to each other, suggesting that it came from this region on Mars. So this is the first ever detection of a Mars quake, period. But this is the first ever detection of a quake on another planet other than Earth and Mars. So this is really cool stuff that's coming out of a planetary seismology community, and polarization analysis was used in this case. And in fact, the location of a Mars could not have been possible without tools like this. Any questions? Okay. If there are no questions, we have come to the end of the lecture. Let me do a recap. We learned about waves and how we could classify them based on polarization direction and wave direction. We learned that there are two general classes of waves. You classify them in that way, longitudinal and transverse. And sometimes longitudinal and transverse will couple to give you other kinds of waves. On the Earth, longitudinal waves are compressional waves, or compressional waves are longitudinal waves, shear waves are transverse, and surface waves, radial surface waves are a class of coupled longitudinal transverse waves, PSV waves, that are elliptically polarized because of the boundary conditions that come out of the seismic wave equation. We looked at how we could measure polarization using things like rotation, the rotation matrix, the covariance matrix, and applications to understanding near surface velocity, oriented seismometers at the bottom of the ocean, and also measuring anisotropy through SKS splitting. We also looked at applications on planets far, far away, helping us identify planetary quakes and investigating the lunar interior. And in the case of Mars, just using one seismometer and some nifty seismology, we were able to locate Mars quakes. If there are no questions, I think we can move on to preparing for our lab.
So we have one question, and I suspect that as we wrap up, a few more may filter in. So the first question is body wave polarization dependent on the frequency content?
The simple answer is yes, it is. Because you can imagine that the frequency of the wave will give you some sense of the depth at which, or the wavelength of the waves. And if the wavelength of the wave, say for example, say something about the dominant incidence angle, because the incidence angle changes a little bit as you come in to the receiver. So there'll be a slight change in the polarization, as you're moving vertically into the receiver. So there's a slight change in the polarization, but not so much, right? And that change is just in that vertical radial plane, where you've got the incidence angle kind of becoming more vertical as you come into the receiver. So the simple answer is yes. So, but measuring frequency-dependent polarization helps you then to back out the dominant depth at which the waves are interrogating the interior.
Okay, So another question is the covariance matrix method a time domain method, and how do we account for frequency dependent characteristics?
Is the covariance method a what?
A time domain, is the method done in the time domain?
Yes, it's done in the time domain. How do you account for, yes, it is done in the time domain. How do you account for frequency dependence? You just either you bandpass the wave into some, so you take the time series into a frequency domain, do a bandpass filter, and then do the covariance, do the covariance analysis. In that case, what you're seeing is this is the dominant wavelength that you're measuring, essentially that P wave polarization. That's how you account for it. So if you wanted to account for frequency dependence, you just do multiple band passes, right? Hope that helps. An alternative way actually is you do a receiver function method, which strips out the source signature, and then you have your receiver function, essentially the receiver response, at different frequency cutoffs. This is another way authors have done frequency-dependent polarization analysis and use that to do depth-dependent shear or compression velocities, measure depth-dependent shear or compression velocity. If you wanted to follow up on that, I can send you references to those papers.
All right, do we have any further questions before we wrap up? Oh, okay, so how do you distinguish anisotropy associated with the source and the medium?
Anisotropy.
How do you, is there a way to distinguish anisotropy associated with either a source or a medium?
Oh. Source. So okay, so let me try to understand. Source anisotropy. So only rocks are anisotropic, right? So minerals in rocks are anisotropic. But I guess what you're saying is it anisotropy on the source side as the wave propagates to the receiver? Or is this anisotropy, so is the media on the receiver side anisotropic? And how do you distinguish from anisotropy closer to the source or anisotropy closer to the receiver? There are techniques for doing that, and that's why people essentially use SKS phases as opposed to just pure S phases. Because as the S wave goes through the outer core, it will convert it to polarize in the radial direction completely as a P wave. And therefore, any anisotropy inherited from the source side essentially is wiped out. So that's how you kind of distinguish from effects, source side effects, distinguish source side effects from receiver side effects. I hope that's answering your question, if that was the question.
I'm just waiting to see if we get a follow-up here. Okay, someone said source direction determination will be affected by anisotropy and heterogeneity. People are giving me hard words to say out loud today.
And make you read epistles, right? That's cool.
So I'm not sure if that was a question or a statement. It was not a question, it was. So, okay, I think I'm gonna stop recording.